All right, let's get started. Hope everybody had a good weekend. And then Fat Lab this week. Should be pretty fun though. It's a good lab. It will have flame tests again. And so we'll, of course, talk about the lab in more detail on Wednesday. But thinking to safety, you want to wear cotton again on Wednesday for lab. Oh, so it'll be a flame test. But what it is identifying an unknown compound. So like the flame test is now just part of it. But yeah, so there'll be a lot of other tests to figure out this unknown thing. But yeah, open flame, so wear cotton on Wednesday. Any other questions before we get started? And then just keeping an eye on the syllabus because I swear the weeks are flying by. So this is going to be our last chapter before the midterm. So we'll, of course, do chapter 4 this week. Next week is our exam. So this is a mistake on your syllabus. So you guys won't have the lab practicum. There is lab practicum for online people. You know, y'all are here, so I know you're doing it. So you'll just have your exam. And so we'll do review on Monday and then do our exam on Wednesday. And so this might be a good week too for, no, never mind, because we have our lab this week. I was going to say we could do makeups, but we could always try to squeeze in lab makeups on Mondays. But yeah, if you miss a lab. No, sorry. Yeah, I was just saying if we need to make up labs, Mondays would be good times. But yeah, we'll still have a lab that week. Keep on schedule. So just don't forget midterms are coming up. All right, other questions, comments? Yeah, so it'll be a mix of probably multiple choice and free response. And then I do plan on it being open notes so you can use your books, your notes, your resources. So yeah, you'll have everything, all the cheat sheets. So just kind of, you know, can you repeat examples that we've done, kind of follow along. All right, so now we're doing covalent bonds. And we can, of course, recall that we did ionic bonds, and we could write a note, so recall, right? We just talked about ionic compounds, and that was different in that involved the transfer of electrons. And so now we're shifting gears to covalent bonds. And covalent bonds, and often we refer to these compounds as molecules, as in they're one connected structure. And so they are one connected structure since now they share atoms. And so electrons that share atoms are called bonding pairs. And then we'll look at lone pairs. So let's draw this out. And so we can still use our Lewis dot structure to our advantage here. So we start off with oxygen. So how many valence electrons does oxygen have? 6. And then so let's fill in our Lewis dot structure. And of course, right, we want to fill this up appropriately. So 2p, 2s, this is more of an aside. So 1, 2, 3, 4, 5, 6 there. So that's why we have, right, our two group ones and then our one single ones. And so now we can add these definitions. So then we have our 2 electrons that are together. So they're already paired. And so these are our lone pairs, or non-bonding pairs. And then we have these just two lone little electrons here. And so this is where we can make a bond. And then this is also getting to where we'll be going through the trends, but this is hinting to us, right, that oxygen tends to make two bonds. So again, right, two little electrons, so two places to hook up, so two bonds. So I'll put that for now. And we'll go over how many bonds everything can make kind of again, but I just want you to start seeing it. And then we're paired here with our hydrogen. And again, just kind of start with your Lewis dot structure for hydrogen. Let's brighten up the color a little. So hydrogen, one valence electron, right? I put two of them if we're thinking of the formula H2O, right? So that's saying we have two hydrogens. Okay, two hydrogens, one oxygen. So now we're wondering how can they bond and connect. So that's part of what you're going to be learning in this chapter. But again, our hint is we have these little lone electrons. And so let's go ahead. And now I'm just kind of using these half arrows to show single movement. Sorry, I'm a terrible artist. I can barely draw arrows apparently. And so now we're just showing them as our bonding electrons. And so notice when our electrons make a bond, right, we now change the two little electrons to a single line formally. So again, each line is two electrons, and just like we saw, right, each atom is contributing one electron to that bond there. And right, could be written in other ways, so they just explicitly drew the two pairs. We typically won't continue to do that. And so let's look at a few other examples. And so now this can start to explain some of our trends on our periodic table. So for instance, right, hydrogen, well, we just saw that that has one little electron. And we can also think back to the octet rule that we've kind of danced around it, right? We at least have talked about this concept. Well, the electrons want to fill in their shells entirely. Oops. Let me grab a periodic table. Oh, yikes, wrong class. All right, so we said, okay, that they want to fulfill the octet rule, and we talked about it in terms of electron configuration, right, that they typically wanted the electron configuration of these noble gases. In the case of hydrogen, we often call it the duet rule, and that would be hydrogen helium. Of course, helium is already satisfied by 2, and then the rest we kind of simplify with octet. So this concept of 8 electrons to satisfy that. So we'll kind of see that repeated here. And so in this case, right, hydrogen, we're going to find that it tends to be a diatomic, aka it's found like this in nature, since it's not very happy as just this little lone electron. But they can come together, make a bond. Now it's satisfied by the duet rule. And so again, just emphasizing, okay, 2 electrons, so duet rule, satisfied. We can also look at chlorine or bromine, fluorine, so all the halogens, diatomics. So chlorine, bromine. So all these, right, are similar. And so let's just look at one, for example. So how many valence electrons does fluorine have? So 7. Start with its Lewis dot structure. And so again, right, it looks kind of similar to hydrogen. So it just has all these lone pairs, so they're still not going to participate in bonding. And then we have, right, 1 point for connection, so typically likes to make one bond. So now we can, again, see where 2 of them are going to come together. Since that's a stable form. And so now, again, they'll have a single bond between them. And so like I mentioned, we want to start at counting the electrons and show how it's satisfied by the octet rule. So fairly straightforward in this case. We'll highlight this. So 1, 2, 3, 4, 5, 6, 7, 8. So this fluorine feels 8 electrons. And then we can do the same with the other one. So obviously they're symmetric. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, so they're both satisfied by the octet rule. And so now we start to get into, well, how do we, predict the type of bond? Is it ionic? Is it covalent? What's going on? And so that's not always a straightforward answer. Some of it is dictated by the electronegativities. So as we mentioned before, so let's look at a large difference in electronegativity. So again, we said an ionic compound was typically a metal plus a nonmetal. And so what I mean by this is, right, again, this is kind of our typical trend, but then we do find a few weird scenarios, and we can kind of compare the electronegativity, see if that gives us a better picture. But let's just start with sodium chloride. So that's a pretty standard ionic compound. And then you'd have to be given a chart of this, or provided the value. And so if you remember, we talked about the periodic trends. And so recall fluorine, right, was the most electronegative. So electronegativity increases kind of in that general trend. So remember, we said it increases as it goes across, and they get closer to filling the octet. Decreases as it goes down, of course, since the outer shells start to get pretty far away. So, okay, fluorines are most electronegative. Otherwise, right, we can just get our value from the chart. Often fluorine is just rounded up to 4, so we say it's 4, that's the most electronegative. So let me fire up my calculator. So let's test it for sodium chloride. So we look at chlorine over here. So 3.16 minus sodium, so 0.93. So again, you just take the difference of your two values. And then this one is 2.23. And then again, this is just kind of a guide. So it says that if it's larger than 2, generally it's considered ionic. And then as we go down, so we can have kind of polar covalent. And so what does this mean now, polar covalent? So remember what I had said about electronegativity, right? That it's like how much it's pulling in a bond. And so this is a nice depiction of what's going on. So maybe this is HCl. So we have chlorine here, hydrogen. So again, chlorine is more electronegative, and that just means it has a tendency to pull those electrons towards it. And so it has a greater sphere here showing the greater electron density. And then hydrogen is again kind of stripped here and left partially positive, since again it doesn't have a lot of electron density around it. So that's what it means to be polar. And then later, as we progress in the course, we'll see the influences of this polarity. Let's just test out the math for now, and then we can test out one that I don't know how it'll work out electronegativity wise, but I do know that it's a funny one. So let's do, so we do HCl, so chlorine 3.16 minus H, so 2.1. And so now that's under 2, but then their cutoff is greater than 0.4 for nonpolar. So it's right there in that polar covalent range. So again, right, just a guide. There are other ways to measure polarity too that we'll talk about. And then if we have a nonpolar covalent bond, then we have more of an even sphere here. Electrons are shared equally. And so this would be the case of chlorine or fluorine, right, any of our diatomics. And so even though each one of these is very electronegative, right, if your difference is 0, then you're going to have a nonpolar bond. All right, maybe let's look at a strange one. Well, this is, yeah, this would be a good one. So let's look at aluminum chloride. So we have aluminum chloride. And why I bring this up is because this would actually not be a good one to test y'all on for the naming convention, because, right, you might be confused about it. So aluminum plus chlorine, right, you could put aluminum in the metal category. It's right on the stair-step line on the other side. So metal plus a nonmetal, at least you might think so. Let's check the electronegativity difference. I think it'll actually work out. So 3.16 minus 1.61. And so that is under 2, which honestly I wasn't sure how it would come out. But the other thing that I want to mention is, again, yes, this is a guide, but how do you definitively tell? And so that goes back to the crystal structure. And so at some point, right, somebody has to crystallize it, characterize it. And this is actually its true nature. So you can see it's not even quite what we expect. And later we'll even get into that, right? So we'll talk about the geometry in a second. But this is what it is in the solid state. So again, this is only a reflection in the solid state now. It could have different behavior in gas or solution that people could try to study. But from this, we can tell that it is, yes, more of a covalent compound. And then it does this weird bridging stuff, which you can maybe tell that that helps it get to 8 electrons. Otherwise, it's actually electron deficient as aluminum chloride. And then this is what I mean by it's a bad one to test on, because this one, because of the confusion, right, metal plus nonmetal seems very ionic, so aluminum chloride is accepted. Aluminum trichloride, this is the covalent naming, so we'll learn that today. So that's also appropriate. And then for some reason, they also specify the oxidation state in some of these naming conventions. So I'm just trying to show you there's historical reasons for the confusion and the strange naming, and so you may come across that. So that's where the discrepancy comes from. Oh, and this is a good See, this is what I was meaning, that they can study it at different phases. And so apparently at the gas phase, it would be the monomer. And like I said, we'll talk about the expected geometry, which is trigonoplanar if we draw it as such, which again is only in the gas phase apparently. So all this is just to say, right, you have to kind of study a compound deeper so you can really understand its nature. All right, so again, this is just a guide. Main point here is that we just take the difference in electronegativity of two elements if we're trying to calculate that. All right, and so again, kind of more formalities, so we can just discuss these things. So like we saw, we were looking at single covalent bonds, where again, they're just sharing two electrons, like water here, or we could draw another one. So we'll start seeing a lot of methane. So this is just another common compound, of course. Methane. And, oh, I should explain. So I drew the 3D structure just kind of out of habit. So these are just single lines, again, right, 2 electrons. These are still just single lines, except I drew this one as what's called a wedge, so kind of a little thicker to show that it's coming out of the plane of the board, and then this dash shows that it's going behind the plane of the board. And so geometry will work on this as well slowly. All right, so back to some more diatomics. So let's look at this. So now we can have what's called a double covalent bond, formally. And so if we go back to oxygen, right, we can draw our same Lewis dot structure. So again, we mentioned, right, well, it can make 2 bonds, potentially. So we saw, right, it can make 2 separate bonds. Or, in the case of the diatomic oxygen, O2, and again, we can start to see things. Well, we expect it to have a double bond then, because each oxygen wants to make 2 bonds. And if I went a little too fast, right, draw out kind of both pieces first, put them together, so there's, right, each one going into our bond here. So now we can say, okay, well, this is formally a double bond. And so general trends with double bonds, right now they're sharing more electrons, so they tend to be stronger than a single bond, and shorter, again, just on average. So shorter than a single. So again, if you were doing chemistry research, this would all be things that you would have to characterize, you know, and you would care about what's your average bond length between those 2 atoms typically. Is your compound anomalous, or is it pretty standard? Why? It's that sort of thing. We can think about other scenarios, so it kind of hints to us that elements that can double bond with each other or themselves are carbon, nitrogen, oxygen, sulfur, and phosphorus. So yes, we might see some stuff later. I'll draw just some examples. So we could have, I'll just draw formate. So we can have a double bond, and I'll draw my lone pairs. So again, oxygen, right, likes to make 2 bonds. So bonded to carbon, and our single bonds there. Yeah.
What were some elements that were mentioned for the double bond formation? With the nitrogen case, are they talking about the diatomic of nitrogen or any element that might bond with nitrogen?
Yeah, so just nitrogen might make like 2 bonds or 3 bonds, yeah. Yeah, so the case of nitrogen, let me just look it up so I don't draw it. Yeah, so nitrogen is funny. So we'll get to it in a second that it can make 3 bonds. But what it's trying to tell you is that, yeah, it will also kind of do this double bond thing, like so. So this is something that nitrogen can do. So all it's saying is, right, this is a double bond, and that, yes, nitrogen can do that. But then maybe you're already seeing it.
It's
So,
not within nitrogen to nitrogen.
It could be, but the thing is nitrogen to nitrogen, if we're talking N2, so let's skip down for a second. So N2, so nitrogen itself, likes to typically make 3 bonds, but nitrogen's funny. It likes to do all sorts of things. So kind of most simply, right, 3 bonds total. It could be in the form of the triple bond, like it is in diatomic nitrogen, right? So in that case, it does make 3 bonds where they're all sharing. But yeah, in this case, right, still makes 3 bonds total, which is important. But in this case, this would be a double bond formally and then a single bond. So does that kind of make sense, the difference? So it's not necessarily just double bonding. I mean, you might have nitrogen-nitrogen double bonds. The problem is nitrogen-nitrogen, that they're actually explosive compounds once you start doing nitrogen bonds. Yeah, so this is, I'll just show you this. So this is called an azide. And so nitrogen, right, can do some double bond funky stuff. But basically they start to get explosive and reactive, which, I mean, depends what you're trying to do. All right, and then before we move too quickly, let's go back to some of these. So again, we want to see how the octet rule is satisfied or if it's not. So in this case, again, oxygen 1, 2, 3, 4, 5, 6, 7, 8. Okay, octet rule satisfied. And then let's just double check the other side. Okay, 1, 2, 3, 4, 5, 6, 7, 8. Okay, each one, right, satisfied by the octet rule. They're feeling 8 electrons each. Oh, the other thing, so we've been kind of doing this a little quickly, but you always want to account for your total electrons in here. So again, right now it's pretty simple. We just had 6 and 6, right, our valence electrons. So you're really adding your valence electrons, and then you want to double count that. So if I have 6 plus 6, I should have 12. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So then if we compare that to nitrogen, might as well redraw their structure. Oops, that didn't work well. So nitrogen, I think they drew it funny. 1, 2, 3. And so again, right, triple bond. Now we can see, well, each nitrogen had 5 valence electrons, so 5 plus 5. So we have 10 total in our system. So 1, 2, 3, 4, 5, 6, 7, 8. So 8 electrons that this one is feeling. And so same thing. Check this side. 1, 2, 3, 4, 5, 6, 7, 8. 10 total in our system, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So everything checks out. And again, same thing. So we can see some triple bonding. So carbon and nitrogen tend to triple bond. So something like so. Yeah.
And how to do this type of formula within the carbon? carbon to carbon? 'Cause that's one of the things that I used to struggle with, since it's one of the unstable elements.
What do you mean? So like,
Yeah,
yeah, I mean,
no, like carbon to carbon only.
I still don't understand your question, because you can't have just a completely carbon thing unless we're talking about diamond or something, right? But any organic structure, you have CH and O.
Okay, what I'm trying to say is that is it possible to do the bonding between carbon to carbon?
But isn't that what I've shown here, a triple
No,
bond
like
here?
excluding the hydrogens, just only carbon.
No, I'm telling you that it doesn't exist, right?
Oh.
So then, because then you have to go back to the allotropes. So what allotropes exist of carbon? C60, but those are all single bonds, right? Graphene might have double bonds. I'd have to think about the structure. But right, so yeah. So maybe I don't quite get what you're asking either, but yeah, because once you go back to just purely carbons, then you just have to think allotropes.
Okay.
I'm drawing organic structures at this point. So yeah, there's limitations, obviously, right? Like you're not just gonna have like triple bonds galore. Everything's gonna be a mix. So you have to think about like where these are found, you know, different drugs or. Right, so let's keep going. All right, so now we want to look, like I mentioned, at kind of the trends that they typically make, right? So we're just looking at small molecules. And so we can be thinking about electron configuration too. I'm mainly going to be drawing the Lewis dot structure, but we're just seeing these trends and how to predict them. And hopefully it'll get, you know, predictable. That's what it should feel like. So we'll start with group 4. So I always say our classic compound is methane, right? CH4. And so carbon has this kind of special hybridized structure. And so we know that carbon always makes 4 bonds. And again, like we're seeing, right, they could be a single, double, triple, whatever combination. Just has to have 4 total. And
Can you do?
yeah,
Can you do carbon monoxide for me?
carbon monoxide.
Yeah.
Yeah, so carbon monoxide. So let's do that one together. Well, let's go. Let's take it aside. Carbon monoxide is kind of a funny one to start off with in some ways. All right, so if we want to do carbon monoxide, so how many valence electrons does carbon have? And then how many valence electrons does oxygen have? And so then we have to think, how can we connect them? Which is not always intuitive. And so we can kind of play with it. So we have, right, 10 electrons total to play with. Maybe we want to start with a double bond. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. And so then we want to check some things about it. So let's first check that we satisfied the octet rule. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, that looks good. Same thing with oxygen. 1, 2, 3, 4, 5, 6, 7, 8. All right, so this is a funny one to start off with because there's something funny about this structure. Well, we haven't talked about what. So let's go ahead and talk about this. So we have what's called our formal charges. And formal charges is, again, just like another way to help us analyze a structure. And in this case, it's going to tell us some deeper information that we're not really aware of right now. And so it could tell us hints about reactivity. It tells us whether our structure is good, bad. So there's a lot of different ways. It's just another way to analyze it. And so normally we would say we want to minimize formal charges, aka we don't want formal charges, but it happens. Our formula for formal charges is we take our number of valence electrons for each element, so like just from the table, and then minus, I say number of electrons, aka each individual electron, so you count it up, like these would be 1, 2. You can see other versions of the formula where it'll say like 2 times the lone pairs, or like minus 1/2 the bonds, or minus 1/2 the bonding electrons. But those are confusing, so I just say minus the number of electrons and minus the number of bonds. So just counting, right, how many things are attached to it. And so if we do it in this case, so we have carbon, and let me draw it out for us. So we have carbon, so 4 valence electrons, again just from the periodic table, minus, so it has 2 electrons stuck on there, minus 3 bonds, so -1 formal charge. Then we repeat that for oxygen. So again, 6 valence electrons minus 2 stuck on there, minus 1, 2, 3 bonds. So 1 plus formal charge. And then you write your formal charges with little circles kind of showing that. Now, does anybody recognize what's funny about this? So what's...
Usually the number tells us the negative charge.
Mm-hmm. And so this is true, right? So the nonmetals, or oxygen, is the most electronegative element, is the other way to look at it. Out of these two, it should be carrying the negative charge. This is one of those funny ones. So then this starts to go into like, could you draw a better structure? And I mean, so you could try to play with it. So what you could try to do is, what if you moved? So it's best to think about these electrons in pairs. And so let's just say, can we do better? And so this is where I want to emphasize, like sometimes, right, this isn't a straightforward process. You could get a wrong answer. You could, you know, play around with it. That's the whole point. So as long as we have 10 electrons, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, we still have that. But then what happens to the structure now? What gets worse? So we fixed our charge rule, our formal charges, and we can go through that analysis together. So write our formal charge on carbon, so 4 minus 2 minus 2, so that's 0. And then this is 6 minus 1, 2, 3, 4 electrons minus 2 bonds, that's 0. But what's the problem? What have we broken now? Yeah, so now we've broken the octet rule. So this only has 1, 2, 3, 4, 5, 6. So 6 electrons that it feels. This has 1, 2, 3, 4, 5, 6, 7, 8. So oxygen's happy, but carbon is not. And so this would be one of those cases on an exam, I'd probably accept both answers, or I'd want you to write kind of both. But really, this is actually the better structure and truly reflective of its behavior, which is interesting. And so this again goes back into like where you come up with some guesses potentially, but then if you had extra information, and again, y'all wouldn't know this, but actually carbonyls, and now I'm going to draw a super toxic compound, but it's simple, so I'm going to draw it. So this compound exists. You wouldn't want to work with it because it's a liquid metal compound that is very heavy, so heavy such that, you know how we have those fume hoods in lab? Well, normally they're rated to suck in stuff, but nickel tetracarbonyl is so heavy that it would float out of the fume hood, and then you would breathe in nickel tetracarbonyl. The nickel tetracarbonyl would decompose in your lungs, leaving you with nickel in your lungs, and then obviously secondary CO poisoning. So fairly toxic, really difficult to work with. You can't work with it in a regular glove box either. Most glove boxes are positive pressure, so that would be kicking your nickel carbonyl out, so you'd have to have a special glove box that operated under slightly negative pressure. Anyways, all that's to say that the carbon attaches to the metal. So AKA the electrons are being donated from the carbon to the nickel, which is odd, right? Again, we might have expected to be bound from the oxygen, but no. This is actually, again, reflective of its reactivity. Yes, carbon is carrying the negative charge, and then it's going to go on to react. All right. Sorry, that ended up being a really long answer to your question, but did that help with CO? All right, so let's go back to the patterns. And so let's look at other typical group 4 compounds. And so we could also substitute this H out for any, like halogen. So carbon tetrachloride is another typical compound. This compound was used a lot in NMR spectroscopic techniques because you can see it has no hydrogens. So before they made deuterated solvents, or before deuterated solvents were more readily available, this was considered the best way to take an NMR, because NMR only looks at the protons, so this would be silent. But I believe it's pretty carcinogenic. So, and then the rest of the group tends to follow pretty similarly. So silicon tetrachloride is a compound, obviously tetrabromide, tetrafluoride, although you wouldn't want to work with the fluoride compound. That would make HF. So that'd be nasty. Silicon tetrachloride is pretty reactive. It's an angry fuming liquid that reacts with the water in the atmosphere to make HCl. And germanium and tin are pretty similar. And so germanium can also be 2-coordinate, not as common, but does exist, is isolatable. Silicon is actually also isolatable, just very unstable. So you could have germanium as well. As such, the heavier analogs get more stable. Don't forget you have tin as well in there. So tin would also make typical compounds like that. Oh, and then don't forget your electrons. All right, so group 5. So first we'll look at kind of the normal group 5 stuff. So kind of more normal. And again, looking at our Lewis dot structure, we see that it wants to typically make 3 bonds. So I'll save the weird stuff. Or we could mention it. So our typical compound is ammonia. So that's our classic kind of group 5 example. I should have brought my molecule kit now, thinking about it. And so it's pretty similar to our tetrahedral geometry. So maybe let's kind of add that in. So these are all tetrahedral. So this is pretty common. And I think I only make you know, and of course you can have your notes and stuff. You only have to be familiar with a few shapes, so I won't test you on all the shapes. But tetrahedral is pretty common, right? We mentioned that in the structure of diamond as well. And then ammonia is pretty similar. It would just be as if we had replaced one of these hydrogens on methane with a lone pair. So now we just have a lone pair instead for nitrogen. So lone pair. I'll have to bring a cheat sheet, or maybe I'll print it out during the break, just so we can see kind of the difference, because this lone pair is also going to occupy more space, so more electron repulsion. So it kind of makes this angle a little smaller than it is for the tetrahedral. So tetrahedral is, I believe, 109.5 or so. And then these are going to be a little smaller, but like I said, I'll print out a cheat sheet. And then we have, so similar compounds, so phosphorus right under nitrogen can do very similar reactivities. So we have phosphine formally, and this is super reactive. So I'll kind of hint at what else it can do. So eventually these group 5 can make a few expanded octets, but like I said, we'll retouch on this expanded octets. But again, kind of hinting at the reactivity, you see this little lone pair, so it's not innocent, and it can go on to make oxygen bonds. So phosphorus really likes to make oxygen bonds. And so again, you can have other typical compounds, so phosphorus trichloride. This would be another angry fuming liquid. So phosphorus trichloride. Arsenic would have the same thing, so arsenic trihydride, or again, right, substitute any halogen. So pretty typical there. And, oh, I forgot to list the geometry. So like I said, right, it's just a permutation of tetrahedral. And so now you can think about the shape. So it kind of looks like a pyramid still. So this is trigonal pyramidal, or pyramidal, however you want to pronounce that. All right, so I put a D there, like a pyramid, you know. All right, let's actually take a break there. All right, so we'll take our little 10-minute break, and then we'll keep going. Like I said, we'll look at kind of the more normal bonding situation, and then we'll hit back on the expanded octet stuff and some of the weirder varieties. All right, quick break, 10-minute break or so. So yeah, as you come back from break, I printed out this website, so compoundchem.com, just VSEPR and the shape of molecules. So we can go through how to use this, but we'll kind of revisit this back and forth. So we have this key, and so electron pairs is either like how many lone pairs or how many like things like atoms are attached to it. So we haven't looked at any good linear examples yet. For 3, we can think of aluminum chloride, so that would be one example. 4 electron pairs, right, like CH4 methane. So there's our tetrahedral structure. And then we can see how to kind of alter it. So we have 4, this BP means bonding pairs. And then if we go over, right, this looks like ammonia. So ammonia has 3 bonding pairs and 1 lone pair. And so that's what I mentioned about the bond angle, that it's going to be just a little bit smaller. And then, well, let's look at our next example then. So looking at group 6, kind of some typical compounds. So of course our classic example is water. Oops, drew that crazy, sorry. Maybe we should start back with the Lewis dot structure, right? Typical Lewis dot structure. So we say, yes, they like to make 2 bonds, either kind of individually or drawn as double bonds. So other good structures, so we can look at CO2. I'll draw out CO2 for y'all. So again, you can see, right, our oxygen making 2 bonds typically, carbon still making 4, although in this case, right, 2 double bonds there. If you are keeping electron bookkeeping in your head, right, carbon is 4 valence electrons, 2 oxygen, so 6 times 2, so 12 plus 4, 16 electrons total. Again, just so you can keep that in mind, that's what we have here. You can do a quick, right, octet check, so 1, 2, 3, 4, 5, 6, 7, 8 for oxygen. Carbon's the same, 1, 2, 3, 4, 5, 6, 7, 8, and then of course symmetric. And then this one, so I'll point out, right, this is a linear example. So 1 thing in the middle, 2 atoms that it's bonded to, right? It doesn't matter the other stuff, so we know it's linear. And then, so other typical structures. So I feel like I've mentioned CS2 in this class. So this is CS2, of course, right? The analog of carbon dioxide. And again, right, this can be slightly toxic if you ingest it. I think I mentioned that the iron sulfur has a pretty high binding affinity, so it's also difficult for your body to expel CS2. And of course, right, sulfur and selenium have pretty similar reactivity to oxygen, so we can see selenium dihydride like so, or sulfur dihydride. We kind of mentioned, again, those oxygen double bonds to carbon. Look at other drugs. Oops. I was trying to look at the structure. Here we go. Oh, that was a little too crazy. All right, this goes into expanded octets, which we'll look at kind of later. So this is weird. We can dissect it here. So this is sulfonamide. So I don't know if you've ever taken like sulfa antibiotics. So this is what it looks like. What's kind of interesting about this, and again, right, it just shows us the reactivity, how we can keep interpreting it. So kind of imagine sulfur here, right? Instead of lone pairs, well, look, those lone pairs went ahead and reacted with oxygen later. But then it has, right, our two bonds there. So we can just see what sulfur does. And then, again, this is just a nice structure to look at, so we can just, again, see the type of bonds that we're seeing, right? Nitrogen is kind of in the middle of these ring structures. I was hoping for nitrogen double bonds, but here we go. So here's, right, a nitrogen. So it still has 3 bonds, but again, right now it has 2 to this carbon. So remember, this is carbon, 1 of the oxygen. Again, we have oxygen in its typical 2-bond fashion, right? It would have 2 lone pairs on there. So again, just kind of thinking about that. And so let's look at our group 7. So again, just our classic compounds, and then we'll look at funny stuff. And so like we typically saw with hydrogen, again, they generally want to make 1 bond. We'll see some weird expanded octet stuff, but again, that's not typical. Let's pull up another drug. Oh, I misspelled it too badly. Prozac. There we go. So fluorine is pretty important for drug development. So fluorine kind of acts like a methyl group, and this just helps it cross the blood-brain barrier. And so again, this is just to show you kind of a typical bonding structure where you have these 3 fluorides, right, attached to a carbon there. So again, they're just making single bonds, pretty typical. So like I said, there's a lot of medicinal chemistry that's focused on how do you get fluorines on there to potentially make better drugs. And again, right, most of the halogens have that typical pattern, again, if they're going to be involved in a covalent compound. So I'll draw some examples. So again, we kind of saw them. We could draw chloroform. Now I forgot how many chlorines chloroform has. I think it's only 1. So again, 1 bond typically. All right. Any questions so far on what we've covered? All right, so now let's look at some funny stuff. So let's start with, so we'll start with group 8, right? And so of course we mentioned, well, group 8 typically doesn't react, right? This is going to be your noble gases. And so again, this could be a little weird, a little forcing. And then the other thing that I want to mention is, probably this textbook says it as well, but we're not invoking d orbitals. So we do not invoke d orbitals. And so what I mean by that, in most textbooks, right, they do a very cursory overview of this because they don't want to get into the explanation of it. But usually what they typically say, and kind of the rule or whatever, is, oh, well, once you get past this third row here, now they have d orbitals, so that's why they can do the expanded octets. That is wrong. So that's not true at all. So they are actually still doing p orbitals in bonding. So the p orbitals are involved. So not the d. So the reason for this, it's really just a geometric constraint. And so I think I'll mention that deeper with nitrogen, but it's basically just this row. The second row is too small. It just physically cannot fit the expanded octet. If it could, it would. Again, I'll mention some theoretical compounds and calculations that they've done. But yeah, it's not a d orbital argument. So that's wrong anytime you see that. And if you wanted a really more detailed explanation, we could really get into it, but that's kind of beyond this course. And so let's just look at a few oddities that we'll find. And so again, right, chemists are always trying to force something to happen. And as you might expect, so xenon is kind of the one that has more compounds and has been more well studied. Again, larger, more diffuse orbitals, so they've been able to kind of force it, as opposed to krypton and argon. So of course they're trying to make the analogous compounds, but requires probably more forcing conditions. All right, so then we have xenon difluoride, so we can have different permutations. And so now let's keep track of our electrons. So xenon, of course, has 8. Fluorine, we said, right, it still typically wants to just make one bond. And then if we have 2 fluorines, so there's a few different ways to kind of approach this. Again, you could just kind of, right, start sticking electrons on there of, well, I know I need 2 bonds at least, right, to attach them. And then you could just start counting, so you have to do some bookkeeping. So 8 plus 14, so we should have 22 total in this system. And okay, so we're at, so 8, 16, so 16, 17, 18, 19, 20, 21, 22. So that's how you end up with now 3 lone pairs in the center. Otherwise, right, you could maybe recognize, well, let me take 2 of these electrons and make a bond, since again, 2 fluorines, and they want to connect. Different ways just to think about it. And so we haven't formally gone over the naming, but we can at least start to appreciate the naming. And so like you'll see, maybe you already know this because we did carbon monoxide and then we drew carbon dioxide. So what we're getting at with these covalent compounds is that they can form in different ratios. So we can have xenon difluoride, where we use the di to tell us that we had 2 fluorines. And so then other expanded octets that exist or xenon tetrafluoride. Yeah.
How is xenon dichloride acceptable? Because the way I see it, it's like xenon is having 10 electrons.
So that's why it's expanded octet.
Oh, okay.
So again, right, diffuse orbital, you can force it. So yeah, you can make it do things that are kind of unexpected. So yeah, we could write that. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So yes, just at least note that we have expanded octets. So yes, we expect them to be higher than 8.
Because of the D sharp that is present? Oh, okay.
No, that's the quickest way to trigger me. Again, right, huge does not invoke d orbitals. You will see other references that will say that. They are wrong. They are absolutely wrong. And again, I can prove that to you later, but that will take way too much time from this course. So then we can also have xenon tetrafluoride. And so as you can imagine, so tetra, now that means we could fit 4 fluorines on there. So again, right, depends how you want to approach it. You can just start somewhere, start sketching, do your electron bookkeeping. So xenon 8 electrons, fluorine 7 times 4. So 28, 36 electrons total. And then don't forget all the lone pairs on fluorine. So now we're at 8 times 4, so 32, 33, 34, 35, 36. So now we have the complete number. Maybe highlight those little lone pairs. You could have also seen, again, right, we had 8 valence electrons. So fluorine, again, wants to make 1 bond. So we need 4 electrons involved in bonding, and that left 2 lone pairs over there. And then again, yes, expanded octet. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 in this case. So right, yes, it does have 12 electrons that it's feeling formally, but that is fine. Questions about those? And then, so let's look at other expanded octets. Try and move CO down a little. So then looking back, like we saw, right, our group 5 can do some weird stuff. So we saw that phosphorus likes to make a double bond with oxygen, so that's typical. And again, right, could be sulfur, maybe nitrogen too in another case. But then other things that can happen is, so phosphorus pentachloride is a compound that exists. And so again, this is going to have expanded octet issues. And so now we see, right, all the 5 valence electrons of phosphorus are involved in bonding. And so, of course, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So again, right, feeling 10 electrons. And then just as an aside, so here is a problem with NF5. So people have tried to model it. I'm not sure that if it exists at all in any fleeting state. But basically, they've run the calculations for it. And so again, why it doesn't exist has nothing to do with d orbitals. But the fact that these fluorine bonds here would be really elongated if it were to exist. So again, right, nitrogen is just too small. It just physically cannot fit all those fluorines there. So again, by modeling at least, they've figured out, well, yes, it could exist, again, if it had elongated bonds. Like I said, we'd have to check to see if anybody has gotten it in the gas phase. And so similarly, arsenic would do the same sort of thing. So arsenic pentabromide. So again, has a similar structure. We could look at, let's try one of our polyatomics. So now see if you can draw it on your own now. At least attempt it. So this could be tricky because I haven't quite told you what to do about these electrons, but just think about adding more electrons. So how might phosphate look? All right, I was just kind of seeing what we have drawn so far. And so it looked like, again, right, there's no kind of right or wrong way necessarily when we're just trying to figure it out and sketch it. So it looks like most people started with just our phosphorus and then just trying to sketch out, you know, starting with, okay, we have a single bond to each one. And so let's kind of continue filling that out. So we have to keep track of our electrons. So phosphorus, how many does phosphorus bring? So 5. And then how much does each oxygen bring? So 6. So 6 times 4. And then we had to account for this charge. So I tried to give a little hint. But so when we have our -3 charge, we have to add electrons. So I'd like to put charge or whatever, however you want to note it. And then, okay, well, that means 3. If it had been a plus charge, we would subtract. So then how many electrons do we have? So 6 times 4, 24, what did you say?
Oh, I was saying the total.
Oh, yeah, I didn't hear you. What was it?
32.
So 32 electrons. And so, okay, now let's finish putting them around. And so it looks like we could just fill in our lone pairs, and that will work. All right, so now let's do some analysis on this structure. And so now we have some tricky things. So again, we have this -3 charge. So that means now we are definitely expecting some formal charges. So right, if our compound is 0, I'm not necessarily looking for formal charges. Again, in the case of CO, that was kind of a weird one. But in this case, well, I'm definitely expecting a negative charge somewhere, probably 3 of them. And so let's kind of go through that analysis. And so if we look at it for oxygen, so again, just going through the formal charge, and all of these are symmetric, so it really doesn't matter. So 6 valence electrons minus 1, 2, 3, 4, 5, 6 electrons on there, minus 1 bond. All right, so now we have our negative charge. But now we have, right now we have -4. So I'm kind of expecting there to be a +1 on the phosphorus. Let's double check that. So again, phosphorus 5 minus, so 0 electrons, minus 4 bonds. So yes, that's kind of, again, what I expected. So now our formal charges add up to our overall charge. So these two cancel, and then we're left with -3. Now there's another layer of complexity to this structure. And so again, the problem with this is we're just kind of doing like a guesstimation in a lot of senses. And we're just trying to understand the true nature. And so to really understand these right now, we have like computational chemistry as well and modeling, and that sort of gives us a better example. But this is still powerful. We just have to play with it and kind of make what's called resonance structures. So this is one resonance structure. And so again, kind of the significance of this structure is we're seeing that at any point, the oxygen is going to be the one carrying the negative charge. But then maybe we can draw another structure to reflect it. And I didn't quite look at everybody's, and maybe somebody was getting there or thinking of it. But kind of the hint is if we see these like two opposite charges next to each other, then the thought is, what if we draw a double bond? And again, it wouldn't matter which oxygen I picked, but let's try to move these electrons over in a double bond. So now I'm going to draw this new structure. And again, you want to keep these structures all on your test because they're all relevant. And so now we can draw our structure. So, right, again, I just arbitrarily chose that one. That's fine. So PO. And then everything should be the same still, right? I didn't alter anything, so I'm just kind of copying the rest. And of course, you can always double check your count. All right, so then we still have our formal charges, right, on these oxygens. Again, it doesn't matter kind of which three. But then we can think about drawing all the resonance structures formally. And so that means, right, a complete answer is going to be where you draw all of these structures. So rotating that bond around. Because again, we're trying to say, okay, really the true nature of our phosphate ion is if we could take the average, right? So now we have 1, 2, 3, 4, 5. So kind of 5 bonds divided by 4. So everybody has, right, 1.25 bonds, kind of roughly speaking. Again, right, we're not trying to do computational chemistry. We're just trying to get a sense of our molecule. And so again, right, just rotating this charge around, showing our relevant resonance structures. Again, showing that the negative charge is always on the oxygen. Just rotating around. Let's see. I missed the bottom one. Yeah, one more. So again, right, kind of average, if you could, in your mind, average all these structures, that gives you kind of the true nature of phosphate, right? So we're saying not quite a double bond, but probably a little shorter than a typical single, potentially. From our bond order, negative charge is always on our oxygen, right? So we're going to have our -3 charge. It just gets distributed around to our 4 oxygens kind of formally. So let me just write that. So kind of the average of all these structures reflects the true nature. And so again, that's the other thing to appreciate, right? Chemists are always trying to refine their understanding too of a molecule. How does it really behave? You know, does it do what we think it will do? Kind of all those types of questions. Questions about kind of this one and how to approach the resonance structures. So this will definitely take, right, some practice at home. Like it's going to be a lot of trial and error. Like don't be afraid of that. That's the other point too, right? Is like you can start with any structure and then analyze it and then kind of say, which way do I need to fix it? Does it obey the octet rule? How are my formal charges? Are they minimized? Does it make sense? You know, play with the structures. Don't be afraid to do that. And then of course, I forgot to mention, this one, right, feels 8 electrons formally versus these structures, right, are hypervalent. So again, just things to note, nothing wrong about it. We just want to say, yes, this structure has 10 electrons. Yeah.
What would you like call this? That was practice at home.
These are resonance structures, and we're just making Lewis dot structures. So I think, let me look at the homework. Yeah, that's what the homework is on.
Okay.
So, yeah, we could do more practice. I mean, that'll be what we'll do. But yeah, it's on your homework of the second page of drawing the structures. So some of them are obviously like a lot simpler ones, and then we're doing obviously a little harder ones in this case. So I think the ones on your homework should be simple, but they'll be good practice for you to kind of get the feel, right? Counting the electrons, octet rule, all that. So let's try another kind of strange one maybe. We'll skip over CO so I don't have to keep moving it down. But now let's try out ammonium. Just remember that polyatomic. And so see if you can account for the electron or lack thereof. So see if you can draw me a structure. So what do our structures kind of look like? They could also resemble another molecule from before. What do we draw? Anybody know the shape of it? Does it look kind of familiar? 4 things on it. Yeah, so you should have drawn something that looks tetrahedral. So I'll draw it out and then kind of go over the bookkeeping. So nitrogen, right, brought 5 electrons. Each hydrogen brought 1, so times 4. Then we had to do something with this plus charge, so minus 1. Okay, so now we're at 8 electrons, so then looks something like methane basically. And then again, going through our formal charges, so that leaves nitrogen with carrying it. So that's a good guess just because the hydrogens are all symmetric, but then let's prove it. So 5 minus 4, so yes, our 1 plus is on the nitrogen. And so that's our structure there. And that's fine if you didn't draw the dashes and the wedges. Like I said, it's just force of habit, so I'll tend to always draw the 3D. All right, good. So let's finish up with a few other kind of examples of our expanded octets. Anybody familiar with SF6 and what it can be used for fun stuff? So helium, right, you know what happens when you breathe helium? So what does it do to your voice? Yeah, so it makes it squeaky, right? So helium is very light gas, so it's less dense, so that's why it makes the air less dense, so it makes you squeaky. If you want to go for the opposite effect, and just as a safety warning, I do not really endorse inhaling gases, because, all right, there's always an inhalation risk. But if you were to, of course, safely breathe in a small amount, sulfur hexafluoride makes your voice deeper. So, right, obviously opposite effect, so very heavy gas, and so then it'll be more dense. And so this is kind of the rough structure. This is another good geometry to know, octahedral, very standard geometry. I didn't draw the 3D structure very well on this one. I can redraw it. I'm going to focus on these lone pairs. So I'll just kind of redraw it. So again, these, oh my gosh, went too crazy with fluorine. So silicon, so again, these fluorines are kind of up and down. And then to draw it better, showing that these fluorines are coming out of the page of the board. These fluorines are going behind. So they kind of have a square planar structure in the middle. And then again, those 2 fluorines popping out. And then, yes, right, hypervalent. So now we have 16 electrons that sulfur is feeling there. I want to skip sulfate for now. Well, let's do another weird one. So now, group 7. And so our halogens can do some weird stuff as well. And so kind of the typical compound would be, you see IF3 or ICL3. But if people really want to trick you, they're kind of mean and show this II3, which is kind of confusing. Either way, it doesn't matter. See if you can sketch that out for a second. So all these variations will be similar. So I was trying to figure out the center structure. So this is another one that kind of works depending either way on how you want to think about it, right? We have iodine, it's Lewis dot structure. So we have 7 electrons to kind of play with, right? Let's just say, well, we need 3 involved in bonding at least, leaving 2 left over. Or again, you could just have started drawing a single bond to each. Again, whatever element you picked, fluorine, chlorine, or iodine, they would all give you the same structure. And then, of course, filling in appropriate number of electrons. So 7 times 4, so we should have 28 total electrons in this system. So we did 8 times 3, right, 24, 25, 26, 27, 28. So we also get those lone pairs back out as well. All right, so in our last kind of 10 minutes or so of class, let's see if we can try sulfate, so SO4 2 minus. So this is again another polyatomic. This is our sulfate ion. So see if you can draw the Lewis dot structure for that. So keep trying to make some resonance structures. So most people kind of have this thing with one bond to each sulfur right now, which is a good start, but then how else can you play with it? Do we need one double bond, two double bonds? So keep kind of draw some more structures. Y'all are on the right path. Maybe see if you can calculate those formal charges. So just in the interest of time, I'll start going over it. Like I said, I saw a lot of good structures, right? So this is a perfect starting point of what y'all are doing, of just sticking, right, one bond on there. And then, of course, right, we have to do our electron bookkeeping. So sulfur is 6, oxygen 4 times 6. So 30, and then plus 2 electrons, so 32 electrons. So we could have started like so. And then, so what did you notice about this structure? Or what could you do to it? I saw people making some double bonds, but why? Did we try to calculate the formal charges? So right, that could have helped us in trying our analysis, right? So if we look at our oxygen, and right, all of these are the same, so 6 minus 1, okay, so all these have this -1 formal charge, so we want to write that on our structure. And then if we do our analysis for sulfur, so I'm kind of expecting, right, a +2 charge because we have to have -2 overall. So we have 6 minus 4, so yes, sulfur is carrying the 2+. And so again, that's our hint that maybe we want to make 2 double bonds somewhere. It doesn't matter which 2. I just picked 2 arbitrarily. And so now we want to show that structure. So again, now I'm just drawing 2 of them double bonded. That leaves 2 oxygens, right, single bond. And then we just want to draw, right, our resonance structures. So then just kind of moving those double bonds around. And obviously this gets a little confusing in this case, but right, as long as you just show me on exam, at least like, right, the idea that like you're trying to show me, yes, these double bonds are rotating, they're moving. So this is your other good structure, right? Because now we at least have our formal charges minimized. We could kind of argue, you know, about the validity of this structure with 1 single bond. You know, again, I probably wouldn't say that it's wrong on an exam. as long as you show me the analysis. So that's what I care more about, is can we analyze it, right? So then we'd be left with, and again, I'm doing this kind of quickly since we're running out of our formal class time. But then you want to show, okay, well, I still have a plus charge on that sulfur formally if I only make one double bond. So I'll just say, right, not the best, but okay. Because again, right, that's the whole point of this course. I don't want you to feel like, oh my gosh, I don't know the right answer. I want you to feel like, yes, I can analyze it. I can show you that these are some formal charges. I can keep track of my total electron count. So that's super important. So let's just highlight that. Is like your total electron count. That has to be accurate, right? That's like the number one important thing. Did you put the correct electrons in the system? And then from there, right, like we're kind of seeing, there might be some leeway. So then you're kind of balancing the octet rule versus minimizing those formal charges. If I could spell minimizing formal charges. And so again, right, some of these examples at the end obviously were a little tricky because they require in-depth analysis, but I think your homework will give you good practice. And then just kind of where we're going. So we'll go over the naming on Wednesday. Like I said, we'll hit our molecular geometry again, and then we can just keep kind of practicing those structures. All right, so don't forget cotton clothing on Wednesday morning for lab. And then otherwise, just let me know if you have any questions. See you on Wednesday. And then, yeah, if you have anything to turn in, you can just throw it on there. Oh, yeah. Let me grab a copy. I'll grab it. And then, did you have any? Oh, yeah. I just wanted to ask if you had any idea when you want to feel the reflectional lab. Are Mondays like always out? Yeah. Okay. And then, because I also keep 220 from Tuesdays and Thursdays, from 1:30 to 4:20, but is that early?
I could possibly do Tuesday, I just can't do.
Okay.
Yeah, have the time to do it, but next week I can.
And then, right, because these are the two students that need to make it up. Could you do next Tuesday from 1:30 to 4:20? Yeah, it would just be nice to be two people together, so then you have a partner. And then also,
Yeah, so my class is
so you can make it? Okay, sweet. So let's do next Tuesday then, at 1:30. I'll be the same room, HEC 312. Yeah, so it'll be with my 200 level students, but there's plenty of room in there, so there'll be a table for y'all. Okay, perfect. So that settles it.